Hello all. So in today's session we are going to run through a few basics of triangles. Now some of these are taught in the lower grades, maybe in 7 or 8, but many of class 10 students, they have either forgotten this or maybe they never got this to start with. Irrespective, this needs to be clear before you can get to class 10 triangles. So let's understand a few of these. The first one that we talk about is about the altitude of triangles. Now, interestingly, the word altitude or height of the triangle has some visual perhaps crossing our mind, and in most cases the visual that runs through our mind is that of case 1 that you see. So we have a framework involving acute triangle and a right triangle and an obtuse triangle. When I say framework, I'm talking about the setup that we have, the scope of our discussion. So we are talking about altitude in terms of acute triangle, right triangle and obtuse triangle. So in the first case, which is an acute triangle, you see that the altitude, in this case AP and PA, are inside the triangle, and this is the visual that runs our mind, as I was mentioning earlier. Now this is absolutely correct, there's nothing wrong in this visual, but if this is the only visual that runs through our mind when we hear altitude, then our understanding is incomplete. Not incorrect, but incomplete. Because in the first case, yes, the altitude lies inside the triangle. Absolutely fine. So the altitude of the triangle lies inside the triangle when the triangle is an acute triangle. However, when the triangle is a right triangle, as we have in case 2 here, you would see that AB is the height as well as the side, which means the height in this case is the side, or the side of the triangle is the height or the perpendicular as well. So in this case, the perpendicular, which is the altitude or the height of the triangle, lies on the triangle. Well, preposition in maths. So we talked about inside first and then on. Inside the triangle, on the triangle. Well, the preposition class is not over yet, just in case. So when it comes to the obtuse triangle, that's the third case. This is what some of us may not be very clear about. Let's try and understand this. So in this case, obtuse triangle is where we have an obtuse triangle. In this case, ABC is an obtuse triangle, and you would see that this is an obtuse angle. Now if we talk about the altitude from vertex A to the base of this triangle, which is BC, you would see that the altitude will not lie inside the triangle, because ABC is already an obtuse angle, and if I draw any other line, if I drop any other line from A on BC, then you would see that these angles are even more obtuse. So going to the right of B is not helping at all. We are only increasing the angle. We started off with an obtuse angle and now we are making it even worse. So the only way we can think about a 90-degree angle, and that's what altitude is, the only way we can think about coming up with a 90-degree angle is if we go left, and that's what we have done. When you drop a perpendicular AP on BC, and in this case you would have to have BC extended, as you see here. We have extended this line BC to the left, and the perpendicular AP falls on this extended line. So in this case, AP is the perpendicular of this triangle. Interestingly, for this triangle, the base is BC and the height is AP. If we are to calculate the area of this triangle, it would be half into base into height, and in this case it is BC into AP. Interestingly, the altitude of this triangle lies outside the triangle. So the summary is that altitude of a triangle, which is a vertical line drawn from a vertex to the opposite side, which we call the base, may lie inside the triangle, as in an acute triangle. It may lie on the triangle in case of a right triangle, and it may lie outside the triangle in case of an obtuse triangle. So this is one basic which you will build upon in some more problems that you will solve in class 10 triangles. Great. So the next one that we go over to is another property of triangles. Again, something that you might have been exposed to earlier. You definitely would have been, class 10 students, but which you might not recall, or maybe you know, great if you do. You may just pay attention and run through this if you are not very sure. So this theorem, call it, or this property says that whenever you have two parallel lines, in this case AB and CD, so you see that AB is parallel to CD. So if you draw triangles between these two parallel lines, and let's say they all have the same base, then every triangle that we are talking about would have the same area. Interestingly, triangles on the same base and between the same parallels have equal area. Let's see how. So in this case, we are talking about three triangles, LPQ, which is the red triangle that you see here. And then we have a blue triangle, MPQ, and then a yellow triangle, NPQ. So LPQ, MPQ, and NPQ are our three triangles. You would see that they all have a common base. PQ, PQ, and PQ. So up until here, there is no complication. Everything looks absolutely perfect. Next comes the height. Now in this case, the height is what? It's a vertical line, or it's the shortest distance between the vertex and the side of the triangle which is opposite to that vertex. So in this case, as you would see, it's easy to see in triangle LPQ. In triangle LPQ, let me maybe just shade this triangle. I'm talking about this triangle to start with. The base is PQ and the height is LG. You would see that this is LG and perpendicular, and this is a case of the perpendicular inside the triangle, and this is the height. So we get the area. We'll represent that area by A1, say. Now when it comes to the next triangle, in this case MPQ, you would see that this is an obtuse triangle, and from our earlier understanding, where we understood that an obtuse triangle would have at least one perpendicular outside of the triangle, and that's how we have MH over here. MH in this case is a perpendicular which is lying outside of the triangle, and therefore base still being PQ, the area would be half into base into height, which again comes to A1. So also for the third triangle, which is NPQ. In all these cases, you would see that the perpendicular is always equal to the distance between the two parallel lines, and that is EF. So the conclusion here is triangles on the same base and between the same parallels have equal area. Now we come to the third concept, which is an extension of what we just learned. In this case, you would see that we have AB and CD as parallel lines. Again, AB and CD, this is more or less a similar setup, same setup as we had in the last one. In this case, you see we have two triangles on the same base, and those triangles are PQR and SQR. Very interestingly, as you can see, it is obvious. We don't have to prove geometrically. It is obvious. It just stares at us, in fact, that even though these two triangles have the same area, and how do we say that these two triangles have the same area? Because they are lying on the same base QR, and they are lying between the same parallels AB and CD. So triangles on the same base and between the same parallels have equal area. We just learned this a while ago. So these two triangles have equal area, but you would see that triangle PQR has a much smaller perimeter compared to the other triangle SQR. So what we see is that even though the two triangles are equal in area, their perimeters are different. So perimeter is not really impacted by area. Two triangles having same area may have different perimeters. So in this case, you see how understanding one concept, and that was the previous one, where we discussed that triangles on the same base and between the same parallels are have equal area, how understanding of one concept leads to understanding of additional concepts. Thanks for watching.